probably other ways of writing this sentence. This is just the grammar which seemed natural to me. So, all right. For the most part, I did not use examples from your book, so when you read the book, you should get additional examples, yeah? I believe. All right, so we should also talk about what are called existential quantifiers or universal quantifiers. So an existential quantifier typically uses words like some or there exists, all right? Let's see here. Gentleman in third row with a baseball cap, what's your name? What's your name? What?
Aiden.
There exists an Aiden in this class, right? That would be an example of an existential quantifier. However, it would be incorrect to say that there are all Aidens in this class, right? Because you're not all named Aiden, I'm guessing. Pretty sure. So there's a difference, obviously. There exists versus for all. So existential quantifier versus universal quantifier. When we negate statements with quantifiers, they have a habit of flipping from existential to universal or vice versa. All right, so like if we have the statement all x are y, the negation of that is some x are not y. All right? So like all dogs are mean, I think is the example the book gives. What's the negation of all dogs are mean? Some dogs are not mean. All right. No cats are evil. Some cats are evil. Let's see here. Some cats are not dogs. All cats are dogs. Some Twizzlers are delicious. No Twizzlers are delicious. So this is how we negate. Notice the interplay. You're going from existential. These are existential quantifiers, whereas these are universal quantifiers. Like no is a universal quantifier because you're making a statement about everything, right? If I said no one passes this class, what does it mean about you? It means you don't pass the class, right? But not just you, everybody, right? So no is a universal. This is not going to happen, right? But in fact, I hope that no one fails this class. I think that's pretty likely to happen if you guys just, like do the work and don't have to leave or something. Example 9. Let's see here. Example 9. Write the negation of each of the following statements. Some parks are open. The negation of it? No parks are open. All parks are worth the price of admission. The negation of that? Some parks are not worth the price of admission. All right? No investments outperform inflation is a statement. Its negation. Some investments outperform inflation. If you can find an investment that outperforms inflation right now, let me know. Example 10, write the negation of each of the following statements. Some dogs go to heaven. No dogs go to heaven. That's the negation. No pigs are in space. Its negation. Some pigs are in space. Let's see here. Some roses are not red. Its negation. All roses are red. All right. So this is helpful. You can kind of follow this template when you're negating things. If I had a formula sheet, I'd probably put this on here to help me keep on the straight and narrow. Yep.
In this instance, why was A, no dogs go to heaven and not all dogs go to heaven? Because C is some roses are not red.
Have I messed it up? Let's see here. Some dogs go to heaven. Some dogs go to heaven. I think it's that one, right? So I should say no dogs go to heaven.
So is it always set up like that? Like you can't, like there's certain, the way
I-
that the words are set up is how you know it's a certain.
I think there's more than one way to say it logically.
Yeah.
So like I think there's a way to restate the negation in more than one way. So this is a way. It may not be the only like grammatical way. So I think we'll get more into that next time actually. I'm hoping. Oh, and then finally last, you have some homeworks on a discussion of switches in series or in parallel and their relation to logical or and and. So I want to talk about that homework problem with you right now. So here it is. This is from the WebAssign. Here's the setup for the problem. It tells us in 1939, Shannon wrote a thesis on the application of symbolic logic to switching networks. All right, and basically the point here is that if you have like a wire and you have a switch in the middle, you can think of it as being true or false depending on whether it's closed or open. So like if the switch is closed, it's what? I think it's like true. And if the switch is open, it's like false. Anyway, this circuit branch you could think of as like corresponding to a simple statement. So if you have two switches, right? If you know how circuits work, how can you get current to flow from here to here? What do you need? You need both Q and P to be what? To be closed, right? So they both have to be quote unquote true. They both have to be closed in order for the current to flow. So this circuit is in like one-to-one correspondence with the logical operation of conjunction, right? If you had a pair of switches put in series, that's like an and. On the other hand, if you have a pair of switches like this that are put in what is called parallel, what happens? How can you get current to flow from here to here? Well, if either one of these switches is closed, the current can flow through the closed branch, right? If they're both closed, it can also flow through both branches. The only way that the current fails to flow through this circuit is if both P and Q are both open. This is the same pattern as logical disjunction, right? So what that means is that if you can create a circuit with switches, you can model the logic of and or, all right? So right here, we have this series and parallel networks. And so the way this diagram works is this switch and that switch are like mechanically wired together in such a way that whenever that one closes, this one opens and vice versa. It's like if this is closed, that means that one's open. If that one's open, that one's closed. Because it's P and not P, so they're linked mechanically, all right? So what would the logical combination be here for this circuit diagram? What's that? So yeah, this one up here would be what? This would be, you're saying that would be P and not, not P and R? Very good. That one's not P and R. This one up here would be what? P or Q. And we're putting them both together, right? So it should be like, yeah, not P and R or P or Q. So here's what it looks like explicitly. So we have that not P or Q from the upper branch, right? The conjunction of P and Q from the upper branch, and the did I say conjunction? I meant the disjunction, the or of the upper branch, and this is the and or the conjunction corresponding to the lower branch. But those two things are themselves put in parallel, so altogether it's an or of those two compound statements. Yep.
Why are P and Q not or?
Oh, because as I was just explaining, when they're in parallel, it's like or. See, because in order for this circuit to fail, they both have to be open, which is like both inputs being false. Remember, or is only false if it's both inputs to the or statement are both false. If either one is true, it works. Just like this, if either one of those switches is closed, the current flows. So anyway, we're out of time. Hey, listen, we'll do more of these next time, okay? So thanks, guys.
Good question about homework for your retreat.
Yeah, just a second here.
How you doing, Chris?
Hey.